Hello everyone, my name is Pieter Libin, and today I will discuss our work on deep reinforcement learning for large-scale epidemic control. This work was presented and is currently in press at the European Conference of Machine Learning and was submitted to BNAIC as a short paper. So, as we all know, epidemics cause an important threat, as people get sick and they might even die. We were intimately aware of that due to the COVID pandemic. Of course, they also affect our economies because that people are sick and can't go to work, but also because of the extensive measures that are used to try to mitigate epidemics. Now, prevention is the best way to mitigate an epidemic. This can be done through vaccination, but if this is not available, then the use of school closures or more extreme measures as a lockdown can be used. To inform public health officials, epidemiological models are typically used, and such models can be used to understand what pathogen moves throughout a population, but they also can be used to study the effect of preventive measures on an epidemic. Even with such models, mitigation is a challenging process, and to try to help this, we investigated a new method to mitigate epidemics using reinforcement learning. And the idea is to learn dynamic preventive strategies in an epidemiological model. And we want to present a generic method such that it can deal with different kinds of pathogens. While there are significant similarities between pathogens, there are also important differences, such as, for example, the contact network. For influenza, this will be a direct contact network, while for HIV, this will be a sexual network. So there are important differences that need to be considered. In this work, we will conduct our experiments in the context of influenza pandemic that we try to mitigate, and we will thus use reinforcement learning. Now, to give you a short introduction to reinforcement learning deals with learning to behave optimally in an environment. And in this example, the environment is a video game, and the agent is a person that wants to learn to play this video game optimally by pushing buttons on the controller. So the agent pushes a button of the controller, which we call an action, and upon executing an action, the agent is able to observe the state of the video game by looking at the screen, just like any human player would do, and will receive a reward upon executing the action. So, if we use reinforcement learning for epidemic control, we need to choose an algorithm, and here we choose deep reinforcement learning algorithm, more specifically PPO, and our idea is to learn prevention strategies automatically and do so directly in a large-scale epidemiological model. We conduct here experiments in the context of an influenza pandemic, and we want to investigate how we can use school closures to optimally control the epidemic. So, compared to the video game that we had before, now our environment is an epidemiological model. Our actions constitute out of prevention measures, and we are able to observe the state of the epidemiological model and observe the reward that we get. For example, how well are we controlling the epidemic? So, deep reinforcement learning is a very powerful technique that has been used to do very interesting things over the last few years. However, it is a concern that it is quite simple and efficient. And therefore, we need to create an epidemiological model that balances between model realism and also computational efficiency. And therefore, we constructed a tailor-made epidemiological model that can evaluate epidemics in a very efficient way. The objective here is to model influenza pandemic, and in such a way that we can study school closures in a geospatial context. So that means when to close schools, but also where, in which district to do so. So we create a multi-patch model with 400 patches for each of the districts in Great Britain, and each of these patches is simulated with a simple compartment model, what we call an SEIR compartment model that is age-structured, such that we can simulate school closures in an appropriate way. Now, these different patches are connected via a mobility model, and the flow between the different patches is then simulated using a set of non-homogeneous Poisson processes. Now we evaluated this model to make sure that it makes sense in the context of the swine flu pandemic of 2009. And there we, due to the summer holidays, we observed 2 peaks in the data. So the summer holidays made the first peak made the first peak occur and go down, and then when the schools opened up again, a second peak arose. And what you see here, the vertical bars are the data that was observed during this epidemic, and the blue lines that you see are model trajectories generated by our model. So we are able to obtain a decent fit using our model. So to do RL, we need to define a reinforcement learning environment. So we have a state space where we have an SEIR model for each age group. So this reflects directly to the patch and the internal structure of a patch, and we also keep the budget that we have for closing schools. So each district is given a budget, for example 6 weeks, and if this budget is finished, then the schools can't be closed anymore. So this is also part of our state space. The action space is quite straightforward, opening or closing of schools in a particular district, and the reward is the increment in infections at the time t. And this way we try to excuse me, we try to optimize the attack rate, so the number of infections over time. First, we evaluate our method in a single district, because there we can establish a ground truth by removing the stochasticity from the compartment model and by performing a exhaustive policy search. And we do an experiment with an R0 of 1.8, 2.4, and for different census configurations. So we do it in one district, but we consider different censuses of different districts in Great Britain. And what you can see here is the learning curve for different budgets, and you can see that we quickly converge. And on the right, you can also see some box plots where we learned the optimal policy. We simulated it for 1,000 times. It's the box plot, and the scatter point on it is the actual ground truth. And we can see that our policy that we learned matches the ground truth very well, so that what we learn actually shows that what we learn actually makes sense. Now, to actually see how we can learn a joint policy for multiple districts simultaneously, we investigated the community network of different districts in Great Britain by looking at the commute graph. And then we found a community called Cornwall-Devon that consists of 11 districts in which we attempt to learn a joint policy. To do multi-district reinforcement learning, to learn a joint policy, we use a PPO policy network where the input is the state space of each of the districts that we consider, and an output that is a unit for each district that says either to close or to open schools. When we look at the learning curve for this joint policy, we see that we indeed learn for an R0 of 2.4, we quickly converge, while for an R0 of 1.8, it takes a bit more time to converge, but we are learning something. And if we then compare these learned policies by simulating them several times, so the orange box plot is a simulation of the joint policy 1,000 times, and the blue one is simulation of the 11 districts simulated separately, and then the results are aggregated. So we see that the joint policy indeed can make a difference, and this shows the importance of using policies that consider different districts simultaneously. So that concludes my presentation, and I want to thank the authors. This was a collaboration between the University of Brussels, University of Leuven, and the University of Hasselt. Thank you very much, and I would be very happy to answer your questions at this point.